An invisible architecture shapes everything we see in the cosmos. This is the cosmic web, the largest structure known to exist, a hidden skeleton spanning the entire universe. By the end of this journey, you will know 30 of its most profound and closely guarded secrets. We will uncover why entire galaxies are pulled by an unseen force and what lurks in the vast, empty voids between them. How much of reality itself might just be a grand illusion? This hidden skeleton is the first and perhaps most vital secret of our cosmos. The universe is not a random scattering of stars and galaxies. It is a carefully structured tapestry, and the cosmic web is its fundamental design. This vast framework is the large-scale structure of everything, an invisible architecture that dictates where galaxies can form and how they move through the emptiness of space. But what is this framework made of? The answer lies in a mysterious substance we cannot see or touch, a substance that makes up most of the universe's mass. We call it dark matter. Think of it as the universe's ultimate construction material, an unseen cosmic glue. This dark matter weaves itself into an immense network of filaments, like the strongest ropes imaginable, stretching for billions of light years. These filaments are the true backbone of the cosmos. Where they intersect and tangle, they create dense nodes, powerful gravitational anchors. It is upon this dark matter scaffolding that all the luminous matter, the stars and the galaxies we can actually observe, slowly gathers and builds its shining cities. The glittering galaxy you see in a telescope is not floating freely. It is perched upon a hidden foundation, a single point of light on an invisible thread of dark matter, held in place by a force we are only just beginning to understand. So how do you map something you cannot see? Astronomers have become cosmic detectives, developing brilliant methods to trace the outlines of this invisible architecture. One of their most powerful tools relies on a prediction from Einstein's theory of relativity, a phenomenon known as gravitational lensing. Imagine space-time as a vast, flexible sheet. A massive object, like a cluster of galaxies anchored to the cosmic web, creates a deep dip in this sheet. When light from a more distant galaxy travels toward us, it must pass near this cosmic pit. The dip in space-time acts like a lens, bending the light's path and distorting the galaxy's image. We see stretched and warped arcs of light where there should be perfect pinpricks. These celestial mirages are not mere curiosities. They are direct evidence of immense mass bending the fabric of reality itself. By carefully measuring these distortions, scientists can literally weigh the unseen dark matter, mapping the hidden gravitational wells that define the web's densest knots. Another method is a monumental exercise in cosmic cartography. By using powerful telescopes to pinpoint the precise three-dimensional locations of millions upon millions of galaxies, astronomers can begin to see the pattern emerge. Each galaxy is like a single light on a vast, dark highway system. When you plot enough of them, the grand design becomes undeniable. You see the galaxies clustering along immense, tangled filaments, gathering at crowded intersections, and leaving unimaginably vast voids almost entirely empty. This painstaking process of mapping the visible reveals the silhouette of the invisible. The luminous galaxies trace the shape of the dark matter backbone, just as glitter sprinkled on glue reveals the hidden pattern beneath. These two techniques, one observing how light bends and the other charting where light gathers, together peel back the veil on the cosmic web. They allow us to see the unseeable, transforming an abstract idea into a mapped reality. But what could have possibly created such an intricate, universe-spanning structure in the first place? The answer lies in the faintest echo from the very beginning of everything. This hidden cosmic architecture is not a static sculpture. It is a dynamic, living structure, and its immense gravitational forces are constantly in motion, pulling entire galaxies on a collision course with destiny. Our own Milky Way is caught in this cosmic river, moving at an astonishing speed of over 2 million kilometers per hour towards a specific point in space. This mysterious destination is known as the Great Attractor. It is a colossal gravitational anomaly, a focal point of the cosmic web's power, and it is pulling not just our galaxy but thousands of others in its direction. The sheer force required to move so many galaxies is almost incomprehensible. What could possibly possess such gravitational might? For a long time, the answer was frustratingly out of sight. The Great Attractor lies in a region of the sky obscured by the dense stars and gas of our own Milky Way's central plane, a zone astronomers call the zone of avoidance. It was like trying to find the source of a mighty river while standing in a dense, blinding fog. But science has a way of peering through the veil, using telescopes that can see in X-ray and radio wavelengths which pierce through the cosmic dust. We have begun to glimpse the truth. The Great Attractor is not a single, monstrous object. It appears to be the heart of a supercluster, an immense knot where multiple filaments of the cosmic web converge. This is a node of almost unimaginable density, where the gravitational pull of countless galaxies and an even greater amount of dark matter combines into one overwhelming force. It is the ultimate expression of the web's hidden design, a gravitational anchor point on a scale that dwarfs our local galactic neighborhood. Our journey toward it is a journey into the deepest currents of the cosmic flow, a silent, relentless drift dictated by the invisible threads of dark matter. What other immense structures lie hidden in the darkness, guiding the fate of the universe? This silent, relentless drift of our galaxy exposes the true master of the cosmic architecture. The Great Attractor's immense pull is not primarily from the galaxies we can see, but from the invisible ocean of dark matter in which they are all adrift. This brings us to a secret that underpins the entire cosmic web. Dark matter is not a passive component of the universe. It holds absolute cosmic dominion, providing the essential gravitational glue that binds everything together. Without it, the universe as we know it would simply not exist. Think of the early universe, a hot, dense soup of particles. Ordinary matter, the stuff that makes up stars, planets, and us, was constantly buffeted by the intense pressure of light, preventing it from clumping together effectively. Dark matter, however, was different. It does not interact with light at all. It was immune to this cosmic pressure, allowing it to start collapsing under its own gravity far earlier than anything else. These dark matter collapses formed the very first gravitational wells, the initial blueprints for the cosmic web. They acted as cosmic seeds, and as they grew, their gravitational pull began to draw in the ordinary matter, the gas that would eventually form galaxies. The luminous universe we see is merely tracing a pattern that was already etched into the fabric of space by this unseen substance. The filaments of the web are not made of galaxies. The galaxies are like decorative lights strung along pre-existing dark matter cables. The vast voids are not empty because galaxies avoided them. They are empty because the dark matter scaffold never formed there, leaving no foundation for anything to build upon. This dominion is so complete that the shape and movement of every galaxy, the very rotation of their spiral arms, is governed by the gravitational grip of its surrounding dark matter halo. We are all living in the invisible empire of dark matter, and its silent rules dictate the fate of the cosmos. But if dark matter is the invisible framework, what then fills the unimaginably empty spaces between its threads? These vast, empty spaces are the next great secret of the cosmic architecture. If the filaments of the web are the universe's superhighways, then the voids are its desolate, intercontinental deserts. They are not just empty pockets, they are the emptiest places in existence, regions of staggering nothingness that can stretch for hundreds of millions of light years. To cross one of these voids, even at the speed of light, would be a journey of profound and utter solitude. You would pass through an immensity of near-perfect blackness, a cosmic vacuum so complete that you might encounter only a handful of isolated, lonely galaxies in all that unimaginable distance. But what makes these voids so profoundly empty? The answer is more unsettling than you might think. It is not that matter simply decided to avoid these regions. The truth is, these voids are empty of the very thing that builds the cosmos, dark matter itself. The cosmic scaffolding, the unseen skeleton, was never erected here. Without the gravitational foundation of dark matter to act as a cosmic anchor, there was nothing to hold onto the ordinary matter, the gas and dust that forms stars and galaxies. That material was simply drawn away, pulled by the immense gravitational tides flowing toward the dense filaments and nodes of the web. The voids are not just empty of things we can see, they are empty of the things we cannot see. They are true negative spaces in the universe's grand design, defined by an absence so complete it shapes the structure of everything else. This emptiness is not passive, however. It exerts its own strange influence on the galaxies that border it. A galaxy living on the edge of a void experiences a gravitational imbalance, with almost nothing pulling it from the empty side and the full mass of the cosmic web pulling from the other. It can be slowly nudged, even pushed, away from the void and toward the crowded filaments. This creates a subtle but powerful effect, a cosmic repulsion born from a lack of attraction. The voids are actively shaping the web as much as the web defines them. So when you look up at the night sky, remember that the darkness between the stars is not just an empty backdrop. You are peering into the deepest voids of the cosmic web, a glimpse of the ultimate nothingness that helps define our something. How did these immense pockets of nothing come to be in the first place? These immense cosmic voids and the dense filaments of the web are two sides of the same coin, born from the same ancient process. The blueprint for this entire structure was actually drawn in the first fleeting moments of the universe. We have to travel back to a time before atoms, before even the first particles, to a fraction of a second after the Big Bang. The entire cosmos was a searing, microscopic point, and within it, tiny quantum fluctuations were occurring. These were random, minuscule variations in density, little more than hiccups in the fabric of the newborn universe. As the universe exploded outward in a period of incredible expansion called inflation, these quantum whispers were stretched to astronomical sizes. Those microscopic overdensities became the seeds for the future dark matter filaments, while the underdensities were inflated into the vast, empty voids. The entire cosmic web, with all its grandeur and emptiness, is essentially a quantum fingerprint magnified to a cosmic scale. The pattern we see today, spanning billions of light years, was imprinted by the tiniest of random tremors at the dawn of time. This means the location of every galaxy and the emptiness of every void can trace its origin back to a random fluctuation smaller than an atom. Our place in the cosmos was decided by a quantum lottery held in the first instant of creation. And what grew from those ancient seeds are the most fertile regions in the known universe. The filaments of the cosmic web are the universe's true stellar nurseries. These are not mere threads of dark matter, but vibrant, flowing rivers of primordial gas. Within these dense cosmic highways, the raw material of creation is constantly on the move. Vast reservoirs of hydrogen gas, colder and denser than anywhere else in space, stream along these filaments, pulled by the immense gravitational tides of the dark matter backbone. This is where the magic happens. As these colossal flows of gas converge and collide, they trigger a frenzy of creation. The gas clouds begin to collapse under their own weight, fragmenting into vast, swirling nurseries where millions of new stars can ignite at once. Think of it as a cosmic conveyor belt, feeding gas directly into the hearts of growing galaxies. A galaxy perched on a filament is like a city built at the confluence of two mighty rivers, receiving a constant, fresh supply of building materials. This is why these filaments are the most active and productive regions in the entire cosmos. They are the engines of galactic growth, the places where new suns are born at a ferocious rate, lighting up the dark matter framework with brilliant young light. Without these flowing currents of gas within the filaments, galaxies would starve, their star formation sputtering out. The entire luminous tapestry of the universe depends on this constant, silent flow along the hidden threads of the web. But what happens when these cosmic rivers of gas reach their final destination? That faint cosmic blueprint we just discussed left behind a permanent photograph of itself. We can actually see the infant universe and the first hints of the web imprinted on the entire sky. This ancient light is known as the cosmic microwave background, a ghostly afterglow from the Big Bang that fills every direction in space. It is the oldest light we can observe, a snapshot of the cosmos when it was just 380,000 years old. At that time, the universe was not dark. It was a brilliant, hot fog of plasma glowing with an intense, uniform light. But this glow was not perfectly smooth. Thanks to incredibly sensitive space telescopes, we have mapped this ancient light and found it is mottled with tiny variations in temperature, minuscule hot and cold spots. These fluctuations are incredibly small, differing by only about 1/100,000th of a degree. Yet these tiny imperfections are the most important baby pictures ever taken. They are the direct imprint of those primordial quantum seeds. The slightly denser, hotter spots are the regions where dark matter had already begun to pool, the future nodes and filaments of the cosmic web. The colder, emptier spots were destined to become the vast cosmic voids. This map of the early sky is a perfect predictor. When we compare this ancient baby picture to the maps of the modern cosmic web, the patterns match. The hot spots in the microwave background align perfectly with the superclusters of galaxies we see today. The cold spots correspond to the great voids. This means the entire fate of the universe's structure was already set in stone, or rather in light, when the cosmos was only a toddler. The invisible architecture was already there, written in temperature differences so slight they are almost impossible to comprehend. The grand design did not emerge by chance. It grew directly and inevitably from a specific pattern laid down at the beginning of time. But if this pattern was set so early, how did the dark matter begin to weave its threads across the expanding universe? The faint pattern in that ancient afterglow reveals an even deeper secret. It points directly back to the universe's very first second of existence. In that unimaginably brief sliver of time, something extraordinary happened, an event that would dictate the fate of all future structure. This event is known as cosmic inflation, a period of faster-than-light expansion that stretched the newborn universe from a subatomic speck to a macroscopic cosmos in a fraction of a nanosecond. During this violent growth spurt, the quantum world and the cosmic world became permanently linked. The universe was a seething, energetic foam, and within it, tiny quantum fluctuations were constantly bubbling into and out of existence. These were random, microscopic variations in energy, temporary hiccups in the fabric of reality itself. Under normal circumstances, such fluctuations would be insignificant and would quickly vanish. But inflation acted like a cosmic amplifier. It stretched these quantum whispers across the entire sky, freezing them into the fabric of space and magnifying them to astronomical proportions. A random, microscopic overdensity that was smaller than a proton one moment could be inflated to a region light years across the next. This process imprinted a specific signature onto the universe, a pattern of slightly denser and slightly less dense regions. Those amplified overdensities became the gravitational seeds for the dark matter filaments, the future backbone of the cosmic web. The underdensities were inflated into the vast, empty voids. The entire grand design, the architecture that would one day host galaxies and stars, was not created by chance. It was directly stamped onto the cosmos by the random quantum tremors of its birth. This means the specific arrangement of the web we see today, the location of every supercluster and the emptiness of every void. can be traced back to a quantum lottery held in the first fleeting moment of time. Our cosmic address was decided by a random roll of the dice when the universe was less than a second old. Even the colossal structures within our observable universe seem to be caught in a larger, more mysterious current. Astronomers have detected a bizarre and controversial phenomenon known as dark flow. Across the cosmos, entire clusters of galaxies, each containing thousands of galaxies, are streaming in a coordinated direction, as if pulled by a gravitational hand we cannot see. This is not the local motion toward the Great Attractor. This is a vast, coherent drift on a scale that defies conventional explanation, a current that seems to flow through the very fabric of the cosmic web itself. The force required to move these immense structures must be unimaginably powerful, and the most startling possibility is that its source lies beyond the edge of everything we can observe. It suggests that the mass distribution of our cosmic web, vast as it is, might be just a small part of an even grander structure, perhaps a supermassive concentration of matter, an immense sibling supercluster, or a titanic knot in the web that lies far outside our observable horizon is exerting its gravitational pull. Think of it as a cosmic tide, a gentle but persistent tug from a shore we cannot see, guiding the motion of galaxy clusters like driftwood on an invisible ocean. This dark flow challenges our understanding of the universe's limits, hinting that the invisible architecture we have been exploring is itself subject to influences from the great, unseeable beyond. What other fundamental rules of our cosmos might be rewritten by forces we have yet to discover? These dense nodes where filaments intersect are the cosmic equivalent of crowded metropolitan hubs. Here, the gravitational pull is so immense that it corrals thousands of galaxies into a relatively small volume of space, creating the largest structures in the universe bound together by gravity, the galaxy clusters. Within these chaotic cities of stars, a brutal hierarchy emerges, governed entirely by the web's relentless gravity. At the heart of these clusters, you often find the most monstrous galaxies of all, giant ellipticals that have grown to immense sizes through a process of galactic cannibalism. These titans do not form in isolation. They are built from a long history of violent mergers, a cosmic feast where the largest galaxy uses its powerful gravity to tear apart, absorb, and consume its smaller neighbors. Imagine a crowd where the biggest individual constantly absorbs the people around them, growing larger and more dominant with each encounter. That is the fate of galaxies trapped in these dense nodes. A smaller spiral galaxy, minding its own business, will have its path altered by the gravitational tides of the cluster. It gets drawn inexorably toward the central giant. As it approaches, the immense tidal forces begin to stretch and distort it, pulling streams of stars away like cosmic taffy. The galaxy's beautiful spiral structure is completely shredded, its stars scattered into a diffuse halo around the predator. Its gas and dust are violently compressed, triggering a final, brilliant burst of new star formation before being swallowed whole. This is not a gentle process. It is a fundamental transformation, a demolition and reconstruction dictated by the invisible architecture of the web. The cannibal galaxy grows not by creating new stars efficiently, but by devouring the hard work of others, becoming a bloated, featureless giant. Our own Milky Way exists in a much quieter suburban filament, but even we are not immune to this cosmic law of the jungle. We are on a collision course with the Andromeda Galaxy, a future merger that will one day create a new elliptical giant, a testament to the enduring power of the web's gravitational design. Even the matter we think we know is playing a cosmic game of hide and seek. Astronomers have tallied up all the ordinary matter, the protons and neutrons that make up stars, planets, and us, that should have been created in the Big Bang. Yet when they count all the visible material in galaxies and clusters, more than half of it is simply missing. This is the mystery of the missing baryons, a huge portion of the universe's normal matter that has seemingly vanished without a trace. It is not hidden as dark matter. This is the ordinary stuff that should be glowing, shining, or at least casting a shadow. So where did it all go? The most compelling answer lies within the very architecture we have been exploring. Scientists now suspect this missing matter is hiding in plain sight, woven into the filaments of the cosmic web itself. These cosmic threads are not just dark matter scaffolding, they are also conduits for a vast, diffuse ocean of incredibly hot gas. This intergalactic material is so tenuous and so scorching, with temperatures reaching millions of degrees, that it does not glow in visible light. It is essentially invisible to our traditional telescopes. Finding it is like trying to see the heat haze rising from a desert highway from 1,000 miles away. But just as we mapped the dark matter, we have found ways to trace this hidden, searing reservoir. By observing how this ultra-hot gas absorbs and distorts the light from brilliant, distant objects called quasars, we can detect its ghostly presence. This faint signal reveals that the filaments are indeed brimming with ordinary matter, a low-density fog that has evaded our sight for so long. This warm, hot intergalactic medium, as it is called, is now believed to be the final resting place for the universe's missing baryons. They were never truly missing, they were just too spread out and too hot for us to easily see. A vast, invisible atmosphere permeating the empty spaces between the galaxies, held in place by the web's immense gravitational embrace. This ability to map the cosmic web across the depths of space gives us something even more profound, a functional time machine. Gaze far enough out into the cosmos, and you're not just looking across space, you are peering back into time. The light from the most distant galaxies has been traveling for billions of years to reach our telescopes. When we observe a filament of the web 10 billion light-years away, we are seeing it as it was 10 billion years ago, a snapshot from the universe's youth. This allows us to watch the cosmic architecture under construction. In the early universe, the web was a far more chaotic and dynamic place. The filaments were narrower, the knots of matter were smaller and more numerous, and the collisions between young, gas-rich galaxies were spectacularly common. We see these proto-galaxies blazing with the light of newly formed stars, lining up along the faint, nascent threads of dark matter. It is a universe in its messy, formative stages. By comparing this ancient web to the mature, settled structure we see in our local, modern universe, we can trace its entire life story. We witness the slow, gravitational consolidation of matter, the way smaller filaments merge to form thicker cosmic highways, and how the most massive galaxy clusters grow by consuming their neighbors, drawing in entire lines of galaxies over cosmic epochs. This is not a simulation, it is direct observation. We are watching the universe build itself in fast forward, seeing the very evolution of the largest structure in existence. The light arriving at our eyes tonight from the depths of space carries with it the entire history of the cosmic web, a story still being written. This hidden cosmic ocean of hot gas holds another, more subtle secret. Woven throughout the vast filaments of the cosmic web are immense, invisible magnetic fields. These forces stretch for millions of light years, creating a ghostly magnetic personality for the entire structure of the universe. We have long known that galaxies, including our own Milky Way, possess their own magnetic fields, but the discovery that these fields also permeate the near-empty voids between galaxies, tracing the invisible filaments themselves, was a profound surprise. So where did these colossal magnetic fields come from? Their origins are thought to be ancient, seeded in the earliest moments of the universe. One leading theory suggests they were born in the violent chaos following the Big Bang, amplified over billions of years by the slow, churning motions of gas within the cosmic filaments. As these immense rivers of primordial gas flow and collide, they can stretch and twist primordial magnetic seeds, strengthening them, much like a dynamo generates a magnetic field from motion. These fields, though incredibly weak by earthly standards, are vast in their influence. They are not strong enough to rip galaxies apart, but they exert a subtle, guiding hand on the very material that builds them. As clouds of gas stream along a filament toward a hungry galaxy, these magnetic fields can channel the flow, preventing the gas from dispersing too widely and helping to funnel it more efficiently into the galactic core. They act like invisible cosmic rails, guiding the raw material of star formation to its final destination. This magnetic influence can even affect how gas clouds collapse to form stars, adding a layer of order to the chaotic process of creation. Without these faint, universe-spanning fields, the journey of gas from the web to the galaxy might be far more erratic and less productive. The cosmic web is not just a gravitational map, it is a magnetized one where invisible forces work in concert with gravity to shape the luminous universe we see. How far back can we trace the story of this invisible architecture? That constant flow of gas along the filaments is not a gentle trickle, it is a direct, targeted downpour. Galaxies embedded within the cosmic web receive a steady supply of fuel through a process known as cold flow accretion. Imagine a galaxy sitting at the intersection of several dark matter filaments, like a city at the center of a vast river delta. Instead of water, these rivers carry streams of cold, dense hydrogen gas. This gas does not heat up and wander aimlessly. It remains cold and coherent, flowing smoothly along the filament's gravitational channel, falling directly into the galaxy's waiting embrace. This is a cosmic rain shower, a continuous infusion of pristine star-forming material. This direct delivery system is incredibly efficient. When this cold gas hits the galaxy's reservoir, it does not need to cool down first. It is ready to collapse immediately under gravity, igniting a firestorm of new star birth. This process is why galaxies in the early universe, and those in dense filamentary regions today, can form stars at such a ferocious, almost violent rate. They are not just using the gas they already have, they are being constantly refueled from the cosmic reservoir flowing through the web itself. Without this cold flow accretion, galaxies would quickly exhaust their internal gas supplies. Star formation would sputter out and the universe would grow dark. This silent, constant rain from the cosmic filaments is what keeps the galaxies shining, turning the invisible architecture of the web into a brilliant tapestry of light. This colossal river of galaxies is known as the Sloan Great Wall. It is one of the largest single structures ever identified by humanity, a filament of the cosmic web so immense it seems to defy the very principles of cosmology. To call it a wall is almost an understatement. It is a continent of galaxies, a sprawling cosmic superstructure that stretches for over 1.4 billion light-years from end to end. Just contemplating its size is a dizzying exercise. If you could travel at the speed of light, a journey across its full length would take you 1,400,000,000 years. Within that incomprehensible span, it contains not dozens or hundreds, but many thousands of massive galaxies, all bound together by the gravitational thread of a single dark matter filament. Its discovery forced astronomers to reconsider the upper limits of how large a coherent structure could actually grow. According to some models of the universe, there is a theoretical limit to the size of such formations, a cosmic scale beyond which matter should not be able to cluster uniformly. The Sloan Great Wall brushes right up against this limit and perhaps even crosses it. It is a structure so vast that its own gravity influences the expansion of space in its local region, creating a pocket of the universe that marches to its own slow, stately rhythm. It reveals a universe capable of engineering on a scale that still manages to shock us, a reminder that for all we have learned, the cosmos retains a capacity for grandeur that can humble our finest theories. Even a galaxy's spin is not its own. The majestic rotation of a spiral galaxy, its billions of stars wheeling around a central hub, seems like a signature of its isolated identity. But this is another cosmic illusion. The direction a galaxy spins, the very orientation of its spiral arms, is often dictated by the immense, invisible architecture that cradles it. This control is exerted through tidal forces, a subtle gravitational pull from the cosmic web's filaments. As a galaxy forms within a filament, the dark matter flowing along that cosmic highway tugs on it from specific directions. This gravitational shearing acts like a gentle but persistent hand on a cosmic top, setting it spinning along a preferred axis. The galaxy's initial rotation is essentially imprinted by the larger structure, its fate written not from within, but by the cosmic currents that birthed it. We see evidence of this in the coordinated spins of neighboring galaxies. In some vast filaments, astronomers observe that galaxies are far more likely to spin in alignment with the filament's direction, like beads on a string all twirling the same way. Their individual fates are synchronized by the vast, invisible thread they all call home. This means the beautiful pinwheel of a distant spiral is not a random dance. It is a slow, stately rotation choreographed billions of years ago by the gravitational tides of the nascent cosmic web, a permanent record of its ancient place in the flow of the universe. The grand design of the cosmic web may owe its existence to the faintest tremors in the fabric of reality itself. These are not gravitational waves from colliding black holes, but something far more ancient and profound, primordial gravitational waves generated in the violent first instance of the Big Bang. Think of the newborn universe as a vast, turbulent ocean. The cataclysm of its birth would have sent powerful ripples moving through the very substance of space and time, oscillations that compressed and stretched the fabric of everything. These primordial waves are theorized to have interacted directly with the distribution of matter and energy in that searing early plasma. As they passed through, their rhythmic squeezing and stretching could have provided an additional organizing force, gently nudging matter into the slight over-densities that would one day become the filaments and nodes of the web. It is a breathtaking concept that the same cosmic ripples we are now trying to detect with sophisticated observatories might have been the subtle chisels that helped sculpt the largest structures we see today. The pattern of the web in this view is not just a quantum fingerprint, but also an echo of spacetime's first vibrations. What if the invisible architecture is not just a static map, but a dynamic structure with its own hidden weather? This grand cosmic architecture faces an ultimate dissolution. The same force that governs the large-scale structure of the universe is also destined to unravel it. We have seen how gravity built the cosmic web, but its future is ruled by a far more mysterious and dominant power, dark energy. This enigmatic force acts as a kind of anti-gravity, causing the expansion of the universe not just to continue but to accelerate. For billions of years, the gravitational pull of the dark matter filaments has worked to gather matter, building galaxies and pulling clusters together. But dark energy is a constant, relentless pressure that works against this cosmic construction. As the universe expands, the gravitational ties that bind the web grow weaker, stretched over ever-increasing distances, while the repulsive push of dark energy grows ever stronger. Imagine a vast spiderweb stretched across an ever-widening chasm. At first, the silk holds firm, but as the gap widens inexorably, the threads become taut, then thin, and finally they begin to snap. This is the fate awaiting our cosmic web. First, the connections will fail. The gentle cosmic flows of gas along the filaments will be severed, starving galaxies of the fuel they need to form new stars. The great rivers of creation will run dry. Then, the clusters themselves will be pulled apart. The gravitational anchors that hold thousands of galaxies together will be overcome, and these great cities of stars will drift into the expanding darkness, their communal bonds broken. Finally, in a scenario cosmologists call the Big Rip, the acceleration could become so violent that it tears apart everything, right down to the fabric of spacetime itself. This would not happen for trillions of years, but the outcome is written into the fundamental laws of our cosmos. The very force that gave the web its structure, gravity, will be defeated by the silent, pervasive energy of the vacuum, leaving behind a cold, dark, and utterly isolated universe. The brilliant tapestry of the cosmos, woven over billions of years, may ultimately be shredded by the invisible hand that now stretches it. The most detailed maps of the cosmic web were not drawn by telescopes, but by banks of supercomputers humming in darkened rooms. To truly grasp how this invisible architecture grew from a quantum whisper to a universe-spanning network, scientists have undertaken the ultimate act of digital creation. They have built entire virtual universes from the ground up. Projects like the Illustris TNG simulation are not mere animations, they are complex computational realms that obey the known laws of physics. They begin with a digital sea of particles representing dark matter, ordinary matter, and dark energy, all set within the conditions of the early universe. Then they press play. The simulation runs for billions of virtual years, calculating the gravitational pull between trillions of particles, modeling the hydrodynamics of gas, the formation of stars, and the explosive feedback from supernova and black holes. We do not just watch a predetermined movie, we witness a digital cosmos giving birth to itself, and the result is breathtaking. From this primordial digital soup, the familiar structure spontaneously emerges. Filaments of dark matter weave themselves across the void. Galaxies form at their intersections, spinning and merging in a cosmic dance that mirrors our own observations with stunning accuracy. These simulations act as a crucial testing ground, a cosmic laboratory where we can run experiments impossible in the real world. We can rewind the tape to see why one galaxy became a spiral and another an elliptical. We can watch how gas flows from the vast voids into the hungry filaments. We can even test what might happen if we tweak the fundamental rules, altering the strength of gravity or the push of dark energy, to see how the web's grand design would change. Without these virtual universes, our understanding would be a collection of still photographs. The simulations give us the motion picture, the full, dynamic story of how the cosmic web built everything we see, a story written not in starlight but in lines of code. Even the light from the most brilliant beacons in the cosmos cannot escape the web's grasp. As the intense beam from a distant quasar travels for billions of years to reach us, it passes through the countless filaments of the cosmic web. These threads are filled with clouds of neutral hydrogen gas, the universe's most basic building block. And each time the quasar's light encounters one of these clouds, the gas leaves a tiny, telltale mark. It absorbs a very specific wavelength of light, a fingerprint known as the Lyman alpha line. The result is a bizarre and beautiful pattern etched into the quasar's spectrum. Instead of a clean, continuous rainbow of colors, scientists see a dense, dark forest of absorption lines. Each individual line is a single tree, representing one cloud of hydrogen gas the light has passed through. But the entire forest, with its thousands of tangled lines, is something far greater. It is a perfect slice through the cosmic web itself. By analyzing the precise positions and depths of these lines, astronomers can map the distribution of this invisible hydrogen gas in astonishing detail. They can trace the delicate, web-like structure of the filaments, measure their density, and even determine how the gas is moving. This ghostly glow, this cosmic barcode, transforms a single beam of light into a probe that reveals the entire intricate architecture lying between us and the edge of the observable universe. The light does not just illuminate the quasar, it illuminates the web's shadowy skeleton, proving that even the emptiest reaches of space are subtly woven with the faintest breath of primordial matter. Our cosmic story may have begun with the ultimate collapse. One of the most provocative ideas in all of cosmology suggests that our vast, expanding universe with its entire cosmic web could be the interior of a black hole residing in a larger parent universe. This is not science fiction, but a serious, if speculative, consequence of following the mathematics of general relativity to its most extreme conclusions. The singularity at a black hole's heart, a point of infinite density, shares a disturbing resemblance to the Big Bang singularity from which our universe was born. What if they are one and the same? In this mind-bending scenario, the event horizon of that parent black hole would form the boundary of our own observable universe. The intricate cosmic web we have mapped with its filaments and voids would then be the internal structure of this colossal entity. This radically changes our perspective on the web's architecture. The dark matter filaments could be seen as the emergent structure of this black hole's interior, a complex pattern dictated by the specific conditions of its formation. The accelerated expansion we attribute to dark energy might be understood as the natural evolution of space-time within this unique environment. Even the initial quantum fluctuations that seeded the web could be reinterpreted as vibrations or information encoded on the black hole's event horizon at the moment of our cosmic birth. This hypothesis forces us to confront a deeply nested reality, where every black hole in our universe could potentially contain an entire cosmos within it, each with its own cosmic web, in an endless fractal recursion of creation. The grand design we have been exploring would not be the top level of reality, but merely the interior decoration of a single chamber in an immeasurably larger cosmic mansion. This fundamental disagreement over the universe's expansion rate strikes at the very heart of cosmology. Known as the Hubble tension, it reveals a stubborn crack in our understanding of cosmic history. On one side, we have meticulous measurements from the early universe, primarily from the Planck satellite's map of the cosmic microwave background. This baby picture of the cosmos allows us to calculate how fast the universe should be expanding today. On the other side, we have direct observations in our local universe, using pulsating stars and exploding supernova as cosmic yardsticks to measure the current expansion rate. These two methods, both incredibly precise, do not agree. They provide two different answers for the Hubble constant, the number that describes today's expansion speed. This is not a small experimental error. It is a persistent and significant discrepancy, suggesting that one of our most fundamental assumptions about the cosmos might be wrong. The implications for the cosmic web are profound. The web's entire growth, from its quantum seeds to its current grandeur, is modeled on a specific cosmic recipe that includes dark matter, dark energy, and the initial expansion rate. If that expansion rate is different than we thought, the entire timeline of the web's formation must be rewritten. Perhaps dark energy is not a constant force but has been evolving, changing its strength over cosmic time in a way that altered the web's development. Or maybe dark matter possesses properties we never anticipated, interacting with itself or with other forces in a way that subtly shifted the growth of the cosmic filaments. This tension is a cosmic clue pointing toward new physics that could reshape our comprehension of the invisible architecture. The very skeleton of the universe may have grown according to rules we have yet to discover. This grand digital universe built inside our most powerful computers has revealed a glaring cosmic puzzle. The simulations predict a specific population of small galaxies, tiny dwarfs that should swarm around larger galaxies like ours, held in place by the gravitational web. Yet when we look out into our local universe with powerful telescopes, we find a much quieter neighborhood. The vast majority of these predicted satellite galaxies are simply missing. This is the core of the missing satellite problem, a direct conflict between our best models of cosmic structure and the reality we observe. The simulations show that the dark matter filaments of the web should fragment, creating thousands of small dark matter clumps. Each of these clumps should have enough gravity to pull in gas and form a small, faint dwarf galaxy. According to the math, our Milky Way should be surrounded by hundreds, if not thousands, of such satellites. In reality, we have only found about 60. This is not a small counting error, it is a fundamental mismatch. So where did all the dwarfs go? The leading theory suggests they did form, but something prevented them from ever shining brightly. The earliest, smallest galaxies might have been so fragile that the intense radiation from the first stars and supernova blasted away their gas, stripping them of the raw material needed to form stars. These dark matter clumps would still be there, orbiting our galaxy, but they would be completely dark, invisible to our telescopes. Another possibility is that our understanding of dark matter itself needs revision. Perhaps dark matter particles are not completely cold and slow-moving, but are slightly warmer. This tiny adjustment would have a huge effect, suppressing the formation of the very smallest dark matter clumps, and thus eliminating the potential homes for the missing dwarfs. This discrepancy forces us to look deeper, to question whether the invisible threads of the web are woven from a material even more mysterious than we first believed. That ghostly glow from distant quasars reveals a hidden world we could never see on its own. These brilliant beacons are not just distant points of light, they are the universe's most powerful flashlights. At the heart of a quasar lies a supermassive black hole, but it is the activity around this cosmic drain that creates the incredible blaze. As vast amounts of gas and dust spiral inward, the material is compressed and heated to millions of degrees, glowing with an intensity that can outshine an entire galaxy. This fierce radiation blasts out across the cosmos, and on its billion-year journey to our telescopes, it pierces through the dim, ethereal filaments of the cosmic web. These filaments are filled with wispy clouds of hydrogen gas, the basic raw material of creation. Invisible on their own, they cannot hide from the quasar's penetrating beam. As the light passes through, the hydrogen atoms absorb very specific colors from its brilliant white light. Each cloud it encounters takes a tiny, precise bite out of the spectrum. When astronomers finally receive this ancient light, they do not see a clean rainbow. They see a spectrum scarred by thousands of dark absorption lines, a dense forest of missing light. Every single line is a shadow, a silhouette of one hydrogen cloud the beam encountered. Collectively, this Lyman alpha forest is not a random mess, it is a barcode, a secret message that spells out the structure of the cosmic web along that specific line of sight. By decoding the precise spacing and depth of these lines, scientists can perform a kind of cosmic tomography. They can map the density of the gas, trace the invisible contours of the filaments, and even measure how this primordial material is flowing along the dark matter highways. Without the quasar's brilliant, distant glare, these delicate threads would remain forever in the dark, their subtle architecture lost to the void. The universe uses its most violent objects to illuminate its most delicate structures, turning destruction into the ultimate tool for revelation. The silent movements of the cosmic web may soon compose a symphony we can finally hear. Within the dense nodes where filaments intersect, supermassive black holes are constantly merging, events of such colossal power that they shake the very fabric of space-time. Each collision sends out ripples known as gravitational waves, stretching and compressing the universe itself. Right now, these waves pass through us and everything around us completely unnoticed, a silent cacophony of the cosmos's most violent dances. But a new era of astronomy is dawning, one that will tune our instruments to this hidden frequency. The Laser Interferometer Space Antenna, or LISA, is a future observatory that will not be bound by Earth. It will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, forming the most sensitive listening device ever conceived. By firing lasers between these satellites and measuring the infinitesimal changes in their distance, LISA will detect the subtle stretching of space caused by passing gravitational waves. Its primary target is not the brief chirp from 2 stellar mass black holes, but the deep, resonant hum created by the mergers of supermassive black holes, each weighing billions of times the mass of our Sun. These are the giants that dwell in the hearts of galaxies, and when their host galaxies collide at the web's crowded intersections, these black holes eventually spiral together. The resulting gravitational wave is not a quick burst, but a long, low-frequency note that can last for weeks or even months. Thousands of these events, happening across the cosmos at different times and distances, will blend together into a permanent background hum, a gravitational wave background. Listening to this hum will be like hearing the cosmic web breathe. It will reveal the population of these invisible giants in a way light never could, telling us how often galaxies merge in the web's densest knots and how these behemoths have grown over cosmic time. This will be more than just a new sense. It will be a direct, dynamic census of the web's most powerful inhabitants, proving that the universe's largest structure has a voice, and we are just beginning to learn how to listen. The same cosmic filaments that guide galaxies also carry the chemical residue of ancient stellar furnaces. This architecture is more than a map of gravity. It is a vast, sprawling periodic table written across the void. Every element heavier than hydrogen and helium was forged in the hearts of stars or the violent explosions of supernova. For billions of years, these newly minted atoms have been scattered into space, and their journey did not end there. The same gravitational currents that define the cosmic web, the very filaments and voids, have acted as a giant sorting mechanism for the universe's elemental building blocks. Astronomers can now detect the faint spectral signatures of elements like oxygen, carbon, and iron imprinted on the light traveling through these intergalactic threads. It is a cosmic fingerprint revealing a history of star formation and death on the grandest of scales. The densest nodes, the great clusters of galaxies, are often enriched with the heaviest elements, the iron and nickel blasted out from countless supernova over cosmic time. Meanwhile, the quieter, more pristine filaments farther from these crowded hubs might contain a purer, lighter mix of elements, a relic of the early universe before generations of stars had a chance to pollute it with their metallic ashes. This means that by simply mapping the chemical composition of the gas within the web, we can read a history book of cosmic evolution. A filament rich in iron tells a story of a region that has hosted many massive, short-lived stars that died in spectacular explosions. A void with a higher ratio of primordial hydrogen points to a place that has remained largely untouched by the alchemy of stars. The invisible architecture is not just a skeleton. It is a circulatory system for the very elements that make planets and life possible, a permanent record of every star that ever lived and died to seed the cosmos with complexity. Even the oldest light in the universe holds a secret that challenges our most basic assumptions. When scientists created their most detailed map of the cosmic microwave background, they expected to see a random, isotropic speckling of hot and cold spots, a relic of the universe's quantum origins. Instead, they found something deeply unsettling. The patterns are not completely random. They appear to align along a specific axis, a preferred direction in space that has been nicknamed, with a hint of scientific dread, the axis of evil. This name reflects how unnerving this discovery is, as it seems to violate a fundamental principle of cosmology, the idea that the universe should look the same in all directions. It suggests the cosmos might have a built-in handedness, a cosmic north and south imprinted at its birth. One compelling theory is that this alignment is not a flaw in the data, but a fossil imprint. It could be the ghostly signature of the cosmic web's primordial structure, already stretching across the infant universe and warping the distribution of matter and energy on the largest imaginable scales. Think of it as a watermark pressed into the universe's first light by the unseen gravitational tides of the nascent dark matter filaments. This axis of alignment might literally be the central spine around which the entire web first began to spin and weave its threads. If true, it means the blueprint for the universe's largest structure was not just present at 380,000 years old. It was already exerting a directional pull, guiding the cosmos toward its future form. This single, perplexing feature in the ancient sky whispers that the universe may have had a preferred direction all along, a hidden orientation written into the fabric of reality before the first star ever shone. Our very existence is tied directly to the silent architecture of the cosmos. The specific address of our solar system, nestled within a quiet spiral arm of the Milky Way, is not a random cosmic accident. It is the direct result of our place within a particular filament of the cosmic web, a location that provided the perfect conditions for a stable, life-friendly galaxy to evolve. We are the products of a cosmic neighborhood with a very specific history. If our galaxy had formed within one of the dense, violent nodes of the web, where galactic cannibalism is the rule, our story would have been cut short long ago. In those crowded metropolitan hubs, frequent collisions and intense radiation would have shredded planetary systems and made the long, stable periods necessary for life to evolve virtually impossible. Conversely, if the Milky Way had been cast adrift in the profound emptiness of a void, it would have been starved of the raw materials needed to build new stars and planets. Our galaxy would be a lonely, gas-poor island with little of the heavy elements essential for crafting rocky worlds like Earth. Our local filament provided a golden mean. It was dense enough to funnel a steady, gentle supply of primordial gas into the Milky Way, fueling generations of stars, yet quiet enough to avoid the constant gravitational turmoil of the cluster centers. This sustained, orderly growth allowed for the gradual enrichment of the galaxy's gas clouds with elements forged in stellar furnaces. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all cooked inside long-dead stars and scattered by supernova, then gathered by our galactic filament and delivered to the cosmic suburb that would become our solar system. Every atom that makes up our world and us was filtered and sorted by the grand design of the web, arriving at this specific place and time because the invisible architecture guided it here. We are not just living in the universe, we are a spoken word in its vast structural story. These cosmic cartographers are about to receive tools of almost unimaginable power. A new generation of observatories, designed not just to see deeper but to see wider, will soon begin the ultimate survey of the invisible architecture. The Vera C. Rubin Observatory, with its colossal 3.2 billion pixel camera, will photograph the entire visible sky every few nights for a decade. This is not a single snapshot, but a time-lapse movie of the cosmos on a grand scale. It will detect billions of galaxies, charting the fine, wispy tendrils of the cosmic web that current telescopes simply cannot resolve. By watching how the light from these galaxies is distorted over such an immense volume of space, it will produce the most detailed gravitational map of dark matter ever conceived, revealing the web's structure with a clarity we have only dreamed of. Following closely is the Nancy Grace Roman Space Telescope, a cosmic wide-eyed explorer. With a field of view 100 times larger than the Hubble Space Telescopes, Roman will perform vast, deep-field surveys at infrared wavelengths, peering through cosmic dust to see the web's construction in the early universe. It will find millions of galaxies from the epoch when the web was still assembling, tracing the very first threads as they pulled together from the primordial darkness. Together, these instruments will do more than just refine our maps. They will test the fundamental laws of gravity on cosmic scales, probing whether dark energy has changed over time and searching for any strange, unexpected twists in the web's geometry that could point to entirely new physics. We are on the verge of moving from a sketch of the cosmic skeleton to a high-resolution, three-dimensional scan of its every vein and artery, a map that may contain secrets about the universe we have not even thought to question. Our universe might be a ghost, a magnificent projection with no more substance than a shadow on a cave wall. This is the ultimate secret of the cosmic web, the holographic principle, a theory so profound it redefines the nature of reality itself. It proposes that everything we perceive in three dimensions, every galaxy, every filament, every vast void, could be a holographic illusion. The true information describing our reality, the cosmic source code, might be encoded on a distant, two-dimensional surface that surrounds us. Think of the experience of watching a movie on a flat screen. The image has depth and movement, but all that information is stored on the two-dimensional surface of the screen. The holographic principle applies a similar, though far more complex, idea to the entire cosmos. In this view, the three-dimensional universe we inhabit, including the entire sprawling architecture of the cosmic web, is like that movie. It is a projection. The real data, the ones and zeros of existence, are painted on a thin, spherical shell at the very boundary of the observable universe. This would mean that the immense complexity we see is actually a translation, a decoding of information from a simpler, lower-dimensional reality. The dark matter filaments and the brilliant galaxies could be emergent phenomena, patterns that only seem solid and real from our limited internal perspective. If this is true, then the cosmic web is not the fundamental structure. It is the output, the grand and beautiful display generated by a cosmic processor we can never directly see. This idea emerges from the study of black holes, where physicists found that the maximum amount of information a volume of space can contain is not proportional to its volume, but to the area of its boundary. A black hole's entropy, its information content, is defined by the surface area of its event horizon, not the volume within it. The holographic principle simply applies this startling rule to the entire universe. Our cosmos, in a sense, might be the interior of a black hole, with the cosmic web being the holographic projection of data stored at its edge. This would make the web's intricate design a kind of cosmic mirage, a shadow play of unimaginable scale. The very notion of an empty void becomes a fiction, for every cubic light-year of space would be saturated with this projected information, creating the illusion of substance from a flurry of data points. Is the greatest structure we know merely a magnificent illusion, a cosmic tapestry woven from light and shadow on a two-dimensional screen at the end of everything? This cosmic mirage is not just a philosophical idea, it has a mathematical backbone rooted in the physics of black holes. The principle arises from a stunning calculation showing that the maximum information any region of space can hold is not proportional to its volume, but to the surface area of its boundary. A black hole's entropy, a measure of its information content, is defined by the area of its event horizon. Apply this logic to the entire universe and our seemingly three-dimensional reality, with all its galaxies and voids, could be a projection from a two-dimensional surface at the cosmic edge. The intricate cosmic web, in this view, would be a magnificent decoding of data, an illusion of depth and structure generated from a simpler, flat reality. The gravitational forces shaping the filaments and the dark energy stretching the voids might be emergent properties, side effects of this fundamental information processing happening at the boundary of everything. Yet for all its mathematical elegance, the holographic principle faces immense observational challenges. If our universe is a hologram, there should be a subtle graininess to space-time, a fundamental pixelation on the tiniest possible scale, the Planck length. This graininess would leave an imprint on everything, even on the light from distant gamma-ray bursts. So far, our most sensitive instruments have detected no such fuzziness, leaving this core prediction unverified. Competing theories offer their own explanations for the web's nature. Some physicists propose that gravity itself is not a fundamental force but also an emergent phenomenon, arising from the collective behavior of information bits woven into the fabric of space, much like temperature emerges from the motion of atoms. In this framework, the cosmic web is not a hologram, but the natural, dynamic structure that forms as cosmic entropy increases. Another idea suggests the web could be a cosmic crystal, a frozen defect in the early universe's phase transition, its pattern locked in place as space cooled. Each of these theories, the hologram, emergent gravity, the cosmic crystal, strives to explain why the universe looks the way it does. They are all maps, and like any map, they are simpler than the territory they describe. The true nature of the cosmic web remains the ultimate prize, a secret that may require us to rewrite not just our theories of the cosmos, but our very understanding of what is real. This vast cosmic tapestry connects the most immense structures in existence directly to the world we see outside our window. Each of these 30 secrets reveals a universe far stranger and more interconnected than we ever suspected, from the invisible dark matter skeleton to the ghostly magnetic fields and the unsettling possibility of a holographic reality. We have journeyed from the quantum tremors of the Big Bang to the silent, accelerating fate that awaits all things, discovering that the empty spaces are as important as the glittering galaxies. The very atoms that form our bodies were forged in ancient stars and then delivered to this quiet spiral arm by the gravitational currents of the web, making us a living part of this grand design. The next time you find yourself beneath a clear night sky, look up. You are not just seeing pinpricks of light in a void. You are witnessing the glowing nodes of an immense living architecture, a cosmic web that binds everything together. We would love to hear which of these secrets reshaped your view of the cosmos the most. Share your thoughts in the comments and let us know which revelation left you in awe.